Chapter 9 focuses on the topic of disproof, or disproving something. So before, we were always given true statements. So I gave you something that was true, and we were asked to prove it. Now, instead, I'm going to give you some statement, and you're not going to know whether or not it's true or false. So you have to decide first if that statement is true or false. And usually we decide by trying to work through some examples, kind of get a feel for the problem. We can try to prove it, see if we can run into issues. We can try to show that it's false, right? So if it's true, then we're going to have to prove it. And if it's false, we're going to explain why it's false. And when we explain why, right, we're actually going to disprove it. So disproving a statement is proving that it's false. So an important note here, when we prove a statement is false, what we're really doing is we're proving its negation is true. So i.e., when disproving, what we're really doing is we prove the negation is true. So whenever you get stuck trying to disprove something, it's always helpful to think about what its negation is and try to prove that negation. Section 9.1 is talking about disproving universal statements. So we'll actually see two different types of universal statements here. The first one we want to look at is just the basic universal statement for all x and s, p of x. So how do I disprove that? So remember that when we disprove a statement, what we really want to do is we want to prove its negation. So I want to prove there exists some x in S such that the negation of p of x is true. How do I actually go about proving that there exists? We need to show what specific x in X satisfies that negation of p of x. Okay, so when you're showing some specific thing that satisfies the negation, that's called a counterexample. So we use counterexamples to disprove these for all statements. Now it's very important here to remember that we should give a specific example. So a lot of times I see that people want to kind of explain what type of form the example might take or could take, or explain where the examples might come from. But I want you to say, let x equal 2, or consider the set A that has 1, 2, and 3 in it. So you should actually give a specific example as your counterexample. So if you're ever asked to disprove a for all statement, I want a very specific example. And we'll see some examples, some specific examples of giving those specific examples in just a second. Now, before we get to those examples, let's look at one more statement here. I want to think about how to disprove p of x implies q of x. The thing to remember about this statement is that it has that implied for all x in front of it. So this is also a universally quantified statement. So to disprove it, I want to prove the negation. So let's go ahead and write down what that negation is. The negation of a for all is that there exists. And as we've seen multiple times, we want to say that the negation of an implication is the first guy and not the second. So whenever I want to disprove an implication here, you should give a specific x where p of x is true and q of x is false, right? This is the only way to break our if-then. You have the p be true and that q be false. So you give a specific value of x where P is true and Q is false, and that's how we disprove disprove an implication or conditional. Again, I have this specific X, so that's my counterexample. It's an example of the statement being false, an example counter to the trueness of that statement. Okay, so let's look at an example here. So I have this conjecture for every n and z, so for every integer, the integer f of n, which is equal to n squared minus n plus 11, is prime. So a conjecture here, this is just some statement that we're not sure if it's true or false yet. So we call that a conjecture. And we have to determine first if it's true or false. If it's true, we'll prove it. And if it's false, we'll give a counterexample or we'll disprove that statement. So let's go ahead and see if we can determine whether or not this is true or false. So I've got Desmos here to help us, so we can actually compute a lot of values of this. So let's pop into here, and I'm going to put in my function. So we'll say f of x, I'll just call my variable x there, is equal to x squared minus x plus 11. And then we can go into our settings and pull in a table. So now I can look for different values here of x and see what output I get. So when x is -2, I get 17, 13, 11. Those are all prime, 11, 13. So let's see if we can just add some more numbers here. 17 is prime, 23 is prime, 31 is prime, 41 is prime, 53 is prime, 67 is prime. I encourage you to check all these. 83 is prime, 101 is prime, right? So we're looking pretty good with our conjecture. Oh, but then we get to 11, which is 121, and that is not prime because 121 is 11 times 11, right? So we really had to dig deep here to actually find one of these integers that was not prime. But now that we've done that, it's actually really easy to write our proof. So I'm just going to take this Desmos and put it off to the side a little bit here. So I'll pull out that table still, and we can write our proof. So we'll say this statement is false. And now I'm going to give that specific example when n is equal to 11, f of 11 is equal to 11 squared minus 11 plus 11, right? So we can really see those 11s canceling, equals 11 squared, which is not prime. So perhaps we could have used the format of that question. Think about these two things canceling each other. So I'm just left with a square number to help us find that number that was going to give us a non-prime. But this is my entire disproof. It was just that counterexample, so I just needed to give an example where I didn't satisfy the conclusion. So here's one for you to try. You have the following conjecture. If A, B, and C are sets, then A minus B intersect C is equal to A minus B intersect A minus C. So this is very similar to a homework question you have on this week's homework that you worked on in class on Tuesday. So I encourage you to compare this to that homework question and see if you can come up with a proof for it or if you can show that it's not true. So determine if this is true or false. If it's true, give a proof, and if it's false, find your counterexample. So let's go ahead and talk about the next type of statements, existence statements. So now we want to talk about disproving statements of the form there exists an S such that P of X. Okay, so I want to disprove this. And we remember that in order to disprove a statement, really I want to prove its negation. So I want to prove the negation of this statement. What is the negation of that statement? Well, it's that for all x, the negation of P of X is true. So if there does not exist an x such that P of X is true, it means for all of the x's, P of X is false. Now I need to prove something of the format for all. So I can't just give a specific example. I need to show it for all x, not just for a specific x. So it's helpful here to remember that this for all x, p of x, or not p of x statement, is logically equivalent to, so I'll use my logically equivalent to symbol here, showing that if x, or x is in some set, sorry, let me put in that set, if x is in S, then not p of x is true. Right, so we saw that these universally quantified statements are logically equivalent to saying if it's in the first set, so if it's in that S, then not p of x must be true. So then, to prove this if then, I can either use a direct proof, a contrapositive, or a contradiction. And we'll see some examples of that. Okay, let's look at an example here. So let's prove or disprove the following. There is a real number x for which x to the fourth is less than x squared. So here I want x squared to be bigger than x, but x to the fourth to be less than x. So again, perhaps I can use a graph here to help me decide whether or not this is true in sort of my background work. So before I can go about proving it, I need to know whether or not it's true. So let's go ahead and bring in that graph again. And I want to go ahead and graph these two functions. So I'll graph x squared, x, and x to the fourth. And I'm looking for a place where x, which is my blue curve here, is in between x squared and x to the fourth. So I see that x is the biggest between 0 and 1. And then at 1, they all cross each other, and then x becomes the smallest. So we can see from this that there's no point where the x curve, that blue curve, is strictly in between my x squared and my x to the fourth. So I should know that this statement is going to be false. So now we just have to go ahead and disprove it. So to disprove it, we're going to go ahead and write this first as an existent statement. So we know it's not the case that there exists some x in R such that x to the fourth less than x is less than x squared, which means for all x in R, this is really an and, but we're not going to get too sort of deep into that, so I'm just going to say it's not the case that x to the fourth is less than x squared, instead of trying to negate each of those and getting sort of a complicated OR expression. Okay, so I want to try to prove that for all x, this is true. But again, we said that we might want to think about this in terms of an if-then. So if x is in R, then it is not the case that x to the fourth is less than x squared. And now we want to think about proving this if-then. Now, because I have this negation here, I probably am going to want to assume my not q, because not something gives me back an expression that's easier to assume. I'm also going to want to know that x is a real number, because if I don't know anything about x, it's going to be really hard to say anything about what we can do. So I want to be able to assume both not q, or not this, and p. So I should do a proof by contradiction. So we can say, for sake of contradiction, for sake of contradiction, assume x is in R and x to the fourth is less than x squared. Then let's think about what we know here. So I want to be able to maybe divide by x, but I can only divide by positive quantities when I'm working with a square root, with an inequality. So I notice that my x to the fourth, that's always going to be positive or 0. So I know that x to the fourth is greater than or equal to 0, and x is greater than x to the fourth. So x is strictly greater than 0, because it's strictly greater than something that's greater than or equal to 0. Thus, we can divide by x to get x cubed is less than 1 is less than x. And now, whenever I'm dealing with inequalities, we like to be able to deal with things that have zeros in them. So let's try to make this 1 in the middle as 0. So I get x cubed minus 1 is less than 0 is less than x minus 1. And now I notice that I have a term in common between my x cubed minus 1 and my x minus 1, because we know that we can factor that x cubed minus 1 to an x minus 1 times x squared plus x plus 1. So I recognize that I have that factoring available to me. Now, from the inequality we had up here, we got that x was strictly bigger than 1. So since x was bigger than 1, x minus 1 is bigger than 0, so I can divide by that as well. So maybe I should put that in my proof. So I just did this kind of off to the side as I was thinking here. Since x was bigger than 1, x minus 1 is bigger than 0, so I can divide by that x minus 1 to get that x squared plus x plus 1 is less than 0, right, with x bigger than 1. So now I have a positive number, and a positive number, all added together, giving me less than 0. That's a contradiction. So how did I get this contradiction? It came from assuming that we didn't have this statement being true. So therefore, I can conclude that it's true. So therefore, going all the way back, it is false that there exists some x in R such that x to the fourth minus x is less than x. Sorry, x to the fourth less than x is less than x squared. A little low on space, so I put some symbols in there. But right, this is how we could go about doing this. So let's go back over just sort of the basic steps here. We took our statement. We used Desmos to help us try to decide whether or not this statement was true or false. That was just kind of a little bit of background thinking here. After we did that, then we determined it was false. So we wanted to disprove it or prove its negation. We found that negation, we rewrote it as an if-then, and we thought about doing that proof by contradiction. It turns out we could have actually done a contradiction right from the beginning. So instead, I could have just done a proof by contradiction on my conjecture. So let's see what that would look like instead. Okay, so we want to go ahead and do this proof of the same conjecture. In particular, we're going to prove that this conjecture is false using this technique, which is sort of a direct contradiction. So if you want to see a reference for this, this is talked about in section 9.4. So the technique that we're going to use to disprove our statement, to disprove P, is I'm going to assume it's true, and then I'm going to get some sort of contradiction. So let's see what that's going to look like. So I'm going to directly assume the conjecture as it's given. So I'm going to assume there is some x in R with x to the fourth is less than x squared. Now, if you notice, this is exactly what we assumed in the other case when we was doing a proof by contradiction on the conditional that we got from getting a conditional from the for all, and the for all came from negating that there exists. So this is a much more direct way to get to that same assumption. And now I can do all of those same steps. So I can note that x is greater than 0 because it's greater than x to the fourth, which is greater than 0. So we can divide by x. and then I can subtract 1. So I'm doing exactly the same steps I was doing last time, but now I didn't have to do as much work to get to my initial assumption. So that can save us a lot if we just think about doing this direct contradiction instead of doing a contradiction of a conditional that came from a universally quantified statement that came from the negation of an existential statement. Right, so that's certainly a mouthful, but I'm hoping that you can kind of think about those words all together and really make a connection between what we did before and what we're doing now. So what I did, right, I assumed my statement was true. Math, 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 same as before. I got a contradiction. Thus, there is no real number for which the statement is true. So I've disproved it using that contradiction. Okay, as a final discussion question here, I've got a conjecture for you. It says there exists x, y, and z, all greater than 1, with no 2 of which are equal, for which x to the y is equal to y to the z. So go ahead, think about whether or not this conjecture is true. If it's true, prove it. If it's false, disprove it. If you get stuck, you can certainly look in the book. It has a proof or disproof of the statement, but I definitely encourage you to try to determine whether or not it's true or false on your own. So play around with it, see if you can get some intuition for what x, y, and z would need to satisfy, and whether or not it's possible that they exist.